Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the concept illustration problems of level 1. So in this first question, you can see that there is an infinitely long straight current carrying wire which is connected with a semicircular wire, and that semicircular wire is connected to another infinitely long wire going to uh, taking the same current through the complete system. The radius of this semicircular wire is r, and the magnetic field in which it is placed is uniform and is pointing in the downward direction inside the plane, and the value of magnetic field is v. We have to find out the direction of force acting on this complete wire and the magnitude of the force. So we know that this field is uniform and the two ends of the wire are this and this, and if we connect these two ends, then we can say that the shortest length which is formed is 2r, like that. So we can just draw a wire of length 2r, and we can just find out the force acting on this wire. So the direction of the current in this wire would be from A to B. If this end is A and this end is B, then obviously we know that current is going from A to B. So direction of current would be from A to B, and the magnetic field is inside the plane, and therefore we can say that the force acting will be in the upward direction, and F will be equal to I into 2R into B, and direction will be J cap. Okay, and in this case, in the second case, you can see that this is a current carrying loop which is placed in two different magnetic fields. Half of the loop is placed in this first magnetic field which is uniform and pointing inside the plane, and the second half of the loop is placed in this magnetic field which is also uniform, but its magnitude is double and pointing outside the plane. So if we just find out the force on this first half, then we can draw the first half as a equivalent of a straight wire of length 2r, and therefore the magnetic field in which it is kept is inside the plane B, and the current flowing is from bottom to top, like that, I. So the force acting on this wire will be in the left direction, like that. You can check by Fleming's left hand rule, and this F will be equal to I into 2R into B. And the force acting on the other wire, this wire, it can be drawn. I'll just insert a new page. This wire, this half wire, can be drawn like that, and the shortest length of this wire is again 2r, and the magnetic field in which it is kept is outside the plane, and the magnitude is 2r, in fact 2v. So the force acting on this wire will be and the current, obviously current is flowing from top to bottom, so current is flowing in the top to bottom direction, I. So the force acting on this wire is again towards left side, F2, and that force was F1. So F2 will be equal to I into 2R into 2B. So F2 will be equal to 4IRB. So the net force acting on the wire will be F1 plus F2, and it would be equal to 6 IRB. This will be the net force acting on the wire. Now let us move on the next problem. In this question, you can see that there is a current carrying loop carrying the current in this direction. The radius of the loop is r, and the magnetic field is in the radial direction. Now the radial direction means that it is originating from the origin, which is the center of the loop, and it is going radially outwards. And the value of magnetic field is B naught R vector, where R vector is the position vector of that point at which we are finding out the magnetic field. So for example, at this point, let us suppose at this point, the length vector will be in the downward direction and the magnetic field is in this direction, length vector is in downward direction. So we can say that the force acting will be outside the plane. You can check this by Fleming's left hand rule. And in the same way, the force acting on all the elements will be in the outside direction, outside of this plane. So we can just add up all the forces directly. So if this is x axis, this is y axis, then force will be acting in the z direction. And as the fact that force is same, then if we write down the small force acting on the small current carrying wire, then it would be I dl into B. But B at this position, at a distance of capital R from the center, would be equal to this is dl cross B. So B will be equal to I into dl into B. B will be equal to B naught into R, and the direction will be k cap. And if we find out the total force, then we will integrate the force, and F total will be equal to I into B naught into R into dl. Now dl integration, now dl is a scalar quantity, so dl integration will be 2 pi r. You have to remember that I am integrating this df. So integration of dl will be a sum of all the small lengths, which is the scalar sum. So it would be 2 pi r and the direction would be k cap. So F will be equal to I into 2 pi r into B naught r, and direction is k cap. This is the value of F. Now let's move on the next question. In this problem, you can see that there is a current entering in this loop, circular loop, and it is leaving from this point. The total current is I, and the magnetic field is inside the plane of this coil, and the magnetic field is uniform and is of magnitude B. We know that obviously current will be distributed in the inverse ratio of length, because I1 upon I2 will be equal to R2 upon R1. This is the simple analogy of current, electricity. And R2 by R1 will be equal to L2 by L1. And we know that L2 by L1 is 3:1. Okay, so we can say that I1 by I2 will be equal to 3:1, and I1 plus I2 will be equal to I, which is the total current. So I1 will be equal to 3I by 4, and I2 will be equal to I by 4. Okay, and if we just if we have to find out the magnetic force on this complete loop, then we can divide this loop into two parts. The first part is this one, and to find out the magnetic force on this part, we have to draw a shortest length between the two ends, like that. So if we are talking about the force acting on this part, then the direction of current would be from this direction, and the magnetic force will be acting at this direction, F1, and this angle would be 45 degree. Okay, you can check this by Fleming's left hand rule, and F1 will be equal to I into L. L is 2R, in fact root 2R, and magnetic field is B. So this is F1, and if we have to find out the magnetic force on this remaining wire, then obviously the force acting on the remaining wire will be like that. This would be F2, and F2 will be equal to I2 into this I will be I1. Obviously we will substitute the value afterwards. This would be I2, and the current flowing is from this direction. So current is again flowing in this direction, so the direction of F2 will be also same. So F2 will be I2 into length of the shortest length of this loop is again root 2r, and B is the magnetic field. So net force will be equal to root 2r B I1 plus I2, and I1 plus I2 is R. I1 plus I2 is in fact I. So this is the net force acting on the loop, and obviously this force is acting at 45 degrees. So if we have to write it down in vector form, then F net would be equal to IRB I cap with a negative sign plus IRB J cap. So this will be the net force acting on this loop if current is divided in this form. Now we move on the next question.